Hello and welcome to the new episode of Architecture Software Quality Live with Andre. In this episode, we will be talking about debugging embedded systems. Yeah, but before we get into the substance of the episode, let's just talk about what is the embedded system, what is the embedded software that runs on those systems. Normally, you would think of your PC as something that runs a program, and for embedded systems, the program runs not on your PC necessarily, but somewhere else, like on the development board or in a simulator. So I have some examples here, dev boards, like this is a TI dev board, right? This is a STM dev board with a little screen here. So we have, what else do I have? I have BeagleBoard here. So the software actually runs inside one of those boards or inside somewhere else, not on your PC. So debugging those systems is extremely complicated because you have less visibility, right? You have less observability, you have less control over what's going on with that software. So it's a topic that deserves our attention because the more streamlined the debugging experience the developers would have, the faster they are to get the bugs out. And hopefully they are not putting the bugs in. So my guest today is Shawn Prestridge from IR. I'd like to introduce him right now. And Shawn, could you tell us a little bit more about why you are qualified to talk about this topic? Hi, Shawn.
Hey, nice to see you, Andre, and thank you so much for inviting me to be on your podcast. I have been in the embedded industry for approximately 30 years. I started out in Texas Instruments in the calculator group, developing calculators for hardware and firmware that went into the calculators. So I've spent time as a potential customer to IAR systems, so I understand the pains and the motivations of developers and some of the things that you need to be able to take care of. But I've also spent about 13 years now on the tools side. So that means I've seen it from both sides of the coin. And one of the things I really enjoy is helping developers to learn how to use the tools more effectively in order to find these defects more quickly so that they can get their products out to market much faster. So I've spent a lot of time in this industry. And just seen a lot of people banging their head against the wall, and I just really
Mhm.
love the aha moment that they have when you
Mhm.
show them some tool in the toolbox that they didn't even realize was there, where they go, "Oh man, I wish I would have known this about 2 months ago. It would have saved me a lot of time."
Yeah, and so IR and Parasoft are partners. And before joining Parasoft, I've spent about 10 years as an embedded firmware engineer. And we had our tricks to debug it too. We had a debugger, we had this, we had that. So we had a test lab, we have test environment. We had a series of approaches how we can start even debugging a particular issue on the real hardware in the simulator. So you are exposed to a lot more of those situations by the virtue of your position. And over the past, I don't know, like what is it, uh, gazillion years that you've been with IR, like you started in 2008. So what is it,
Since
14
the Earth
years?
was cooling, yeah.
Yeah, yeah. So you probably observed a lot more of those situations, and to notice how people are debugging, how people are getting their job done in a situation where they have to find an issue. So maybe Shawn, you can give us the lay of the land of how do people debug software, embedded software today?
Well, that's a really interesting question, Andre, because from what I've seen, the people tend to fall, or developers tend to fall into two distinct classes. There are those people who are really used to using GCC-based tools or something similar to that, where they're effectively using GDB. And for those developers, it basically boils down to they're using plain old code breakpoints and printf statements because basically they think that's the only tool in the toolbox. And that problem's kind of exacerbated by the fact that most of the free vendor supplied tools are basically just repackaged GCC and GDB. And as the old saying goes, when the only tool you have in your toolbox is a hammer, then every problem looks like a nail. even though that may not be the appropriate tool to use. And what they don't realize is there's a lot more to being able to do embedded debugging than just printfs and using code breakpoints. So, for example, if you're using a proper set of debugging tools, that's both your software debugger as well as your hardware debugger, you get some really cool functionality such as conditional and complex breakpoints. So you can set up the conditions where that breakpoint actually occurs, not just every time it hits that line of code. So if certain conditions are right, then it will breakpoint. You can also do data log breakpoints where you can actually watch the values of variables over time. Uh, Data breakpoints are particularly valuable because, let's say, for example, you're blowing through the top of the stack and you need to find out where am I blowing through the top of the stack. You can actually set a data watch point at the top of the stack, and as soon as you hit that top of the stack, it'll break point the microcontroller and you can see exactly where you are in the call stack before it corrupts any of the global space. On top of that, if you have certain kinds of microcontrollers that have live instruction trace like ARM's ETM, that gives you the ability to see every single instruction that executes. So you can see exactly how you got to that particular point. And that's particularly useful when you're trying to debug something like a hard fault that may occur. Protocol timing issues, nested interrupt problems. It's much, much easier when you have a full instruction trace. But unfortunately, most developers don't really know that those are actually part of an embedded toolbox. And so if your tools don't give you that capability, then maybe it's time to invest in a better toolbox. But that's the typical way that people are doing debugging these days. They either know about all these tools and they're actively using them, and their lives are much much easier because they can find these defects much more quickly, or they simply think that everything's still stuck in the 1980s and the only thing you've got is a printf and a code breakpoint, which changes the timing of the code every time you add it. So can't begin to tell you the number of times I've seen people leave printfs in released code because they said, that's what they tested with, and they really don't want to take it out and retest it because they don't have time in their schedule. So it's
That
it's
is
really kind of interesting.
that is funny. That is funny. Speaking of participation, right there, Erica. Hi, Erica. Erica is posted a comment here. So hi, Erica. All right. So people are dividing in categories. Like some are using GDB, some are using some other tools, some using printfs, and then they're utilizing some hardware capabilities. But in general, like all of those tools are just kind of helping people to do something. So, Shawn, from your perspective, what makes debugging embedded systems such a difficult task that it deserves tools and our conversation today and most of the developers' time that's consumed over there? So what makes it so painful?
Well, part of the problem is that embedded systems in general are very resource constrained. So we're trying to wring every drop of performance out of these embedded systems that we possibly can. And even on the chips that have a more sophisticated debug interface, still the amount of data that you can get out of that per unit of time is incredibly limited. So if you're coming from PC development where you have effectively infinite resources that are available to you, it's actually kind of hard to get into embedded systems because you don't have complete visibility into the system. You can only get little bits of information at a time, and you have to rely on a little bit of experience to know that, okay, if I'm seeing this series of problems, I kind of feel like the problem could be here. Let me selectively use my breakpoints, because that's another issue, that typically you only have a certain number of hardware breakpoints, although some debuggers like ours can give you effectively unlimited breakpoints by actually giving you software breakpoints once you've used up all the hardware breakpoints. But just not having all the full debug capabilities that you would have on a desktop system and all of that visibility makes it incredibly challenging. Not to mention the fact that a lot of times embedded systems are very much event driven. So when you see a defect happen, you definitely saw the defect happen, and maybe you recorded some of it, but occasionally you have a lot of problems actually reproducing the conditions that made that defect manifest itself. And that can be incredibly tricky to do, but there are some techniques that you can use to try to get around those types of problems as well. And that kind of goes into looking at things like code quality, and I'm sure that's a topic that's near and dear to your heart as
Yes,
well.
yes. Hmm. Yep.
So, but
Hmm.
one probably a good
Hmm.
follow-on question
Hmm.
that may be on your list of questions that you
Hmm.
want to ask is, how do I keep defects from getting into my product in the first place? How do I ease
Yeah,
my debugging experience? And the
that's on the
simple
list. Hmm.
but kind of stupid
Hmm.
answer is, don't put bugs in your code in the first place. Now, that's really easy to say, but that's kind of hard to do. But fortunately, there's actually a lot of tools that help you do that as well. And basically, those take the guise of code analysis tools. Um, So basically, you have static analysis, which will look at just the source code of your application. And then you have runtime or dynamic analysis tools that actually instrument your code so that while it's running, it will check for certain erroneous conditions. Now, what these code analysis tools typically do is they draw from rule sets that look at some of the more common pitfalls that developers tend to fall into. And the reason why is, particularly if you're a novice developer, you probably don't know all the rules that there are to be able to write compiler friendly code that makes it produce the most heavily optimized code. And also to basically make your code where it's very cohesive, uses a minimum amount of resources, et cetera, et cetera. You're just kind of writing your code because you're focused on, okay, I'm responsible for implementing this algorithm. So I'm taking this flow chart and I'm trying to turn it into real code. And you're not really thinking about what underlying code structure should I be using? Should I be using this type of loop or this type of loop? So you're kind of focused on what your application is ultimately supposed to do, especially since we basically all have a lot of schedule pressures that are put on us. And so what happens is, code quality tends to suffer a little bit. And what these code analysis tools do is they will go through your code and find some of the more common defects that you might be falling into, saying, hey, you're doing a division operation here, but nowhere did you ever check to see if this divisor is zero. Or there's a path through the code where this variable you're using as a divisor may be uninitialized, so you're going to get random results. And that's kind of exacerbated by the fact that in a lot of silicon manufacturers' example code, they have the divide by zero trap vector turned off. So if you do a division by zero, it just returns zero, and you have absolutely no idea that you just performed an illegal result. And that can be the kind of thing that, when you're working on a pristine set of memory in your application, it works fine. But once it gets out in the field and it's been used a couple million times, suddenly that same set of inputs now elicits a crash lockup problem that you can't really reproduce. So, using those code analysis tools can help you find what we like to call those $1 million bugs inside of your code. But the added benefit to using code analysis tools is that if you can find that defect while you're still desk checking your code and before you check it into a formal build, then it's like the defect never even happened, simply because it doesn't count against your release metrics. But once it gets into a formal build, then every defect is going to count against that release metric, and it's going to forestall you being able to get your product out into the market. So basically, I liken using code analysis tools to kind of like using the spell checker and the grammar checker inside of Word. It doesn't mean that you're going to produce a Dostoevsky, but what it does do is it prevents you from making silly mistakes and helps you to correct them very, very quickly.
Yeah, interesting. Dostoevsky, right? um, so My other question, actually, Lee, you almost answered already. But what are some of the tips and tricks of debugging an embedded system? Like, for example, yeah, don't put the bugs in. We covered that, right? You wanna do code reviews. You wanna do static analysis checks. Sometimes people even tend to create some sort of a test harness just to check to make sure, like unit in a unit testing space, if what they've coded is up to the expectations in that isolated environment. In my experience prior to joining, let's say Parcel, when I was the real developer, I always struggled to just create that test environment and get to that point where the bug occurring or supposed to be occurring. So my time was not actually thinking about what the bug is. My time as a developer was mostly wasted at the, okay, I need to set up all of those conditions. I need to connect the debugger. I need to step through to a certain point. I need to, reset the board gazillion times. So that wasn't the time, kind of significant effort. So what are in your mind, Shawn, tips and tricks that would shorten that pain or shorten that cycle of development idiocracies?
Well, one of the best tricks that I can give you to do that is to write what I like to call linear code, which basically means that you have one statement that does one thing. If you have a single statement of your code that's doing multiple things at a time, that's probably going to be too complicated. And that's for several reasons. Number one, if you write your code linearly where it's one statement does one thing, if you're doing a code walkthrough, it's much easier for people to be able to internalize and understand what that code is supposed to do so they can provide much better feedback. If they look at a line of code and their eyes start to glaze over, they have to spend more than 20 or 30 seconds trying to figure out what that line of code is doing because I love the term self-documenting code. I've heard about this all my life, but it's like a unicorn. I've never actually seen self-documenting code. Um, so embedded developers tend to be particularly bad about not putting comments inside of their code as to what that line of code is doing. But if you write your code linearly, you get relatively close to having self-documented code where it's easier for a developer to understand. And ironically, the easier it is to understand, the more a compiler will actually be able to make better optimization decisions about how that code should be implemented. But also, what happens when you start writing these compound statements is that sometimes you can get into what we like to call the dark corners of the C language specification. So, for example, if you have an argument to a function and inside of there you have nested function calls as the argument, what can happen is that it will, in our compiler at least, invoke a warning that says order of volatile accesses is not guaranteed. So, in other words, what this warning is telling you is that in the C language specification, there is nothing that says that that compiler is going to evaluate things from left to right. So, if you can gain efficiency by evaluating operand 3, then 1, then 2, then 4, and you have it set to a high level of optimization, the compiler is probably going to choose to do that. And so, but these are the kinds of weird things that a lot of developers are not aware of. But when you start writing compound statements, you kind of get into these little weird things that can cause issues, and that kind of leads into what people believe that cranking up optimization introduces bugs into your code. 99 times out of 100, cranking up optimization does not inject bugs into your code. It actually exposes bugs that are already existing into your code. So if your code can run at a high level of optimization the way it's supposed to, that's actually an extra level of testing because you've used good C programming practices and conform to the C programming standard when you can run at high optimization. Because when you crank up that optimization, we get really picky about the language semantics because we use every trick in the book to try to give you that best level optimization. So those are some things that you can do.
Mm-hmm.
Write linear code. Don't try to be too tricky with it. Also, keep in mind, actually, another trick that you can do too that just occurred to me.
Hmm.
We talked about feedback from a code analysis process. Or I should say, we as IAR, wrote a white paper about a year ago, I want to say, where we were talking about the need for code analysis and what it can do for
Hmm.
you.
Hmm.
And in that paper, I actually cited an ACM paper that came from Google that had some very interesting findings. And what they found was that the feedback that you, or I'm sorry, when you get the feedback from that static analysis tool or dynamic analysis tool is equally, if not more important than the actual feedback that you get. And what they found was is that if they took developers that got near instantaneous feedback when they were developing their code, like, they did a desk build and we're trying to check out a module to make sure that everything compiles, if they've got feedback on that code that, hey, you've got this potential problem that's lurking for you, they were 71% likely to treat that feedback as being serious enough that they need to actually go back and check it, and didn't say. But 29% of the time they
Hmm.
said, oh, that's not really an issue, whatever.
Hmm.
But when you make that same feedback available the next day, like it's part of an overnight build where it does the code analysis, that number dropped all
Hmm.
the way down to 20%. So
Wow,
51% drop.
that's.
And their speculation was it's because of the survivor effect, because once you
Hmm.
check that code into the build, like I said earlier, now if you go in and make a change, now it's a defect that counts against your release
Hmm.
metric. So you really want to get that feedback as soon as
Hmm.
possible. But it also has the salubrious effect that if you get the feedback near instantaneously, it's while you're in the zone and you've just
You can.
written that code, and
Hmm.
you know what it's saying, and you're like, oh yeah, let me go back and fix this. I know
Hmm.
exactly where this is. Whereas the next
Right.
day you're drinking your coffee and thinking, what was I thinking when I
Yeah.
wrote this? I don't remember writing this line of
Yep.
code. Are you sure that's mine? So
Yeah. Or getting some review comments like, no.
yeah, or
Yeah.
from somebody else reading it going, what is
Mhm.
this line of code supposed to do? Like, that's a good question. Can I have the next
Mhm.
question, please?
Yeah, yeah, and sometimes it's like the code reviews are focusing on style of code or this and that, and you
Yes.
really want to eliminate the work of your counterparts, right? To
Yes.
review your things that could be automated, right? Could be taken out by the tool. Yeah, we've seen that effect as well. Like,
Exactly. And that goes back to what I said, that if you make it easy for them to understand, they can
mhm.
internalize what that code's trying
Mhm.
to do much more
Right.
quickly and also give you better quality
Mhm.
feedback.
That's true. And to just wrap things up, Sean, it was interesting discussion. I feel like you and I can go on this topic for days, weeks. We
Yeah,
don't
we should
have
have a
days.
follow-on podcast called
Oh,
Coffee with Andre, and we could just keep it rolling.
yeah, and why stop at coffee? Yeah. So,
Exactly.
anyway, so my last question, kind of to wrap things up, is about automation. Right now, what we are noticing that everybody, the game is to automate testing, automate build. Well, first they want to automate build, they want to automate testing, and to check the software as it's being compiled for things like static analysis violations, run some unit tests, run some integration tests, like do all of that as frequently as you can. I know that some of the customers that we have, for example, they're already fully transitioned to this model, and some customers, on the other hand, they're still doing build manual build once a week or something.
Right.
And debugging as an experience, I think, can fall into the same category. So I know that IR has a debugger. So what are the tips and tricks that you can suggest to automate the whole debugging experience? Like maybe, are you seeing that people are benefiting from writing debugger scripts or Python scripts, or maybe kind of give us a little bit of your opinion on that topic?
Yeah, and that kind of falls into the whole thing with continuous integration, continuous deployment. So as you alluded to, a lot of customers are going to this model. um, particularly in some of the more complicated embedded systems that are being developed. So typically in continuous integration, one of the first things they do is code analysis checking. So they have whatever sets of rules that they have. But in addition to that, they'll actually do tests that they've created. This could be regression tests from bugs that have already been submitted against that system. It can also be a series of functionality tests that are developed from the specification that they elicited from the customers. And so what they'll do is they'll actually put the software through its paces in an automated fashion. And so every time you push a change up to the system, it will automatically start going through all of these testing. And I think it's a really salubrious thing. The problem is it kind of puts the onus on some of the quality assurance professionals, the QA people, to basically develop this set of tests. And there's a style of development that's called TDD, or test driven development, that says that really what you should do and the way that you should write your code is to basically write the series of functionality tests that you want it to do, and then start writing the code to basically pass the test. So it's kind of a backwards way of thinking about it, because typically the way that developers have traditionally done it is we write the code, and based upon the specs of the code, we write tests to test the code. But you're kind of turning the sock inside out, and you're kind of cheating because you're writing code that you know will pass the test. But ultimately what happens, though, you get exactly what the customer wants. So it is a viable way to be able to do development, but it hasn't really caught on a whole lot. But I do see more and more
Hmm.
customers starting to use that. But yeah,
Hmm.
there are debug scripts that you can use. We
Hmm.
have a C-SPI macro language that people will invoke
Hmm.
either through Python scripts or batch files or PowerShell scripts. And they'll use that to basically run on real live hardware and collect data and information. So our C-SPI macro language lets you, for example, open a test file on the host PC, read out what the microcontroller should have in terms of register and memory, write it out to the controller, set a breakpoint, run to the breakpoint, stop, pull all the data, the registers and the memory off of the device, put it on a file on the host PC, repeat, and just continually process that. And then they have some other process, usually on a handwritten tool, that looks at what were the registers, what was the memory, what's the correct answer, what am I expecting to see. So it's a little
Hmm.
bit more ad hoc. So you're developing it specifically for that. But
Hmm.
QA people are actually really good at writing testing tools to be able to interpret the data that's coming off of that.
Hmm.
And that's kind of where your tools come in, helping to do code coverage. And you can do code
Hmm.
coverage with ETM and some of our
Hmm.
tools, but your tools go much harder in the paint with being able
Hmm.
to ensure the code coverage and doing full MCDC coverage, that you've executed every single line of code. So there's some really cool stuff that you can do with that. But you have to be very clever about writing those scripts and using the macros and the tools that are available
Hmm.
to you.
Yep.
But kind of going back to what we discussed at the very beginning, it all starts with knowing all the tools in your toolbox. What's
Hmm.
available? How do I use it? When is it appropriate to use it? And that's something that if you're having a hard
Hmm.
time understanding, well, what are all the tools in the debugging toolbox? Well, we actually have some videos on our website that are
Hmm.
part of our YouTube channel that show you how to use them. And of course, you can always contact us, and we'll be happy to get on a one-on-one webinar with you and
Hmm.
and walk through some of the things and to teach you. And we even have IAR Academy that are
Hmm.
classes that you can join either online or in person to be able to teach you all these advanced debugging techniques.
Yeah, and that actually, I think you answered part of the questions I was going to ask at the very end. So if you'd like to have like a minute to kind of point people to the resources, maybe they want to talk to you or the company IR. From my perspective, I know that some of the respected companies that we work with are using IR products successfully. So to me, it's a great indication of a quality and sustainability of your ecosystem. So with that, I'd like to pass it over to you for like a closing remark, and then will finish it off.
Sure. For those of you who aren't familiar with IAR systems, we're actually the world's oldest embedded compiler company. So we started in 1983 on the 8051 architecture, and we've expanded to over 40 different architectures. So no one has been in this game longer than we have. So our compiler technology is based upon our nearly 40 years of experience in this game. And that's why we have Embassy Core Mark world records. But if you want to find out more information about how you can do more effective debugging, I'd encourage you to send us an email at FAE@IAR.com. So that's Field Application Engineer at IAR.com. You can also send an email to me directly. It's just Shawn@IAR.com. You see my name there written down, so you know how to get to me. And just let me know what your questions are, what you're interested in, and what I can do is I can find the correct resources for you so that we can make it where it's easier for you, because we have a lot of information on our website. We have videos, we have links to webinars that we've done, we have tech notes, but sometimes it can be a little bit daunting combing through all that material when you're looking for one little nugget, particularly if you know what you want to do, but you don't know the term that we use for it. If you can describe it to me, I can tell you, oh yeah, this is what we call it, and here's a short video on it. We can talk about it. We can do a webinar, whatever works for you. So yeah, feel free to contact us. We're always here, always happy to talk to you. And that's my pitch. I think you're muted there, Andre.
Oh,
Oh, there you go.
it's a sticky thing.
Hey, at least you know this is live.
That's right. So, Shawn, I think I'll put the contact information there on the bottom of the broadcast. So once it renders, once we post it online, I'll put some comments there with our contact information. But before we close, Shawn, I think we went way over time that I planned for it. However, we have a question. So I'm going to put that question out, and maybe in closing, you can answer that, or we can kind of combine.
Yeah,
From,
I just saw that question.
Mhm.
So what about fault localization techniques?
Yeah,
Well,
what about them?
that's a good question. What would you like to know? No. So typically, the way people have traditionally done it is they will use basically a false position bisection method of breakpoints to try to see where an issue occurs. So probably one of the more common ways that or common questions that we get is, "Hey, I'm running this code and I'm in a hard fault, and I have absolutely no idea where this is occurring." Excuse me. So the way that they'll do that is they'll make an educated guess based upon their knowledge of the code as to where it's going to be. And so they'll set a breakpoint at point A, and then they set a breakpoint at point B. And if they run through the code and they do get to breakpoint A but not to B, then they know it's somewhere in between there. And so they'll move breakpoint A down and move breakpoint B up until they kind of localize on it a little bit easier. Now, if you have ETM trace, this becomes incredibly easy because all you have to do is just scroll through the trace window, and the instruction that executed before you went to the fault handler is the one that caused it. So then you just set a breakpoint there, run back through your test case, and you can very easily find out what the issue is. But you have to be using a device that gives you trace, because not all devices have a trace functionality on it. And you also have to be using a debugger that gives you that kind of trace. But yeah, it does kind of go into the experience of the developers, particularly the ones that develop the code where you suspect the issue might be coming into place. So usually by describing when the defect is happening and what inputs are being put into the system, they can sometimes give you a rough idea of where they feel the defect might be, and that gives you a starting point on where you can start pushing the breakpoints. But it does become kind of tricky in certain cases, but ironically, there are some developers that say that that's the part they love most about
Mhm.
embedded development, is finding that elusive defect, the aha moment when you finally discover it after hours of searching for it. Me personally, I don't know that I go quite that far, but I'd prefer not to have the
Mhm,
bug in there in the first place. But that was kind of what we were talking about a little bit earlier.
mhm.
That if you can keep from injecting those in the first place, then it makes your debugging experience
Exactly.
much easier.
All right. That was a great discussion. Thank you very much, Shawn. I think we went into many topics that I didn't think that we would go into, but it's still a very nice surprise to hear some of the information that I didn't expect to hear, and we're all learning something new. So thank you for being our guest. Um,
Absolutely.
and with that, we'll finish it off and saying bye, bye everybody.